In this video I want to extend our understanding of transformations with matrices beyond just finding the image of single points, but thinking about finding the image of entire equations, so whole lines or curves in the plane. So let me introduce that with or demonstrate that with an example. And here's our example. We want to find the equation of the image of the line y equals 2x minus 3 under rotation by 90 degrees anti-clockwise about the origin, followed by reflection in the x-axis. So notice now we're not trying to find a point, an image point, we're trying to find an entire equation which represents the image of doing something to this original equation or line. So maybe we should try and visualize this. So let's take our equation y equals 2x minus 3. So what's that got? A y-intercept of negative 3. So maybe something like, probably not quite that steep, although that's probably close enough. So there's our original line there, y equals 2x minus 3. The first thing I want to do is rotate the whole thing about the origin by 90 degrees anti-clockwise. So it's going to be at right angles to where it is now. Let me grab a colour here and say, so I reckon it's going to look something like that there. That didn't quite. Let's try that again, just make it go through. So I reckon maybe something like that, when the whole thing's been rotated 90 degrees anti-clockwise, and then we want to reflect it in the x-axis. So I guess reflecting that in the x-axis, that's not too difficult, is it? Still going to have the same x-intercept there, but it's just going to be sloping kind of up that way, so reflected in the x-axis. Alright, so we'll do our matrix operation, we'll get the equation, and then we might graph it maybe on Desmos and see how we go. So let's move that down out of the way a little bit. Alright, so what would be the transformation matrix, the single transformation matrix that we could use to do this composite transformation? So let's talk about the transformation matrix. And we'll call it T. And we'll do this sequence of transformations. Now remember, the order that we write it here has to be the opposite order to the way they're being done. So rotation's happening first and then reflection. So let's write the matrix for reflection first. So in the x-axis that's 1, 0, 0, negative 1. And then rotation by 90 degrees, well that's cos 90, negative sine 90. Sine 90 and cos 90, and those all simplify a lot, don't they? Because what cos 90 is 0 and sine 90 is 1, isn't it? So negative 1, 1. So if we then just take the product of those two matrices, we're going to have a 0 there and also a 0 there, and in the other ones we're going to have a negative 1 there and a negative 1 there. Alright, so that's the single transformation matrix. Therefore, we could say, well, the image point x dash y dash for any point on that line, its image point, actually let's start off, I won't write out the whole matrix, I'll say is equal to t times xy. Now we don't have to do this next step, but the more complex these become, it's going to be probably useful to do it this way, which is to remember that therefore we can write the points x, y in terms of the inverse transformation. So that would be equal to 1 over, so what's the inverse of t here? 0 minus 1 times, swap those two around, does nothing, take the negative of those two, So xy is equal to, now that's going to be 1 over -1, so those 1s are going to become -1s. So if you sort of do that, and I guess I'm kind of skipping a step here because of the space that I've got, but if you complete that matrix multiplication on the right hand side of the equation, then we're going to have negative y dash there and negative x dash there. Alright, so what we've got is x is equal to the negative of y dash and y is equal to the negative of x dash. Now, what that allows us to do is to write a relationship between the, or an equation, which is a relationship between the image points. So we know, let me write it up here, we know that y is equal to 2x minus 3. So in other words, we've got an equation that relates the original x and y coordinates, but we've also now got some equations at the bottom of the left hand side there which relate the original points to the image points. So all I'm going to do is sub in these statements down here where x is equal to the negative of y dash and y is equal to the negative of x dash. So where I have y, I'm going to replace it with negative x dash, and where I have x, I'm going to replace it with negative y dash. Alright, so what do I get? Negative x dash equals negative 2 times y dash minus 3. Now that's an equation which relates x dash to y dash, which is really just an equation for the image, isn't it? So an equation which relates the x and y coordinates of the image points is an equation for the image. So I can say the image line has the equation x equals negative 2y minus 3, and I don't need to worry about the dashes anymore because I'm actually just talking about another equation in the Cartesian plane. The only reason I was using the dashes was to distinguish between the original line and the image line, but now that I'm specifically talking about the image line, I can just use x and y. Or if we were going to write that in y equals mx plus c form, which there should be a negative on there, shouldn't there? Negative x equals negative 2y minus 3. So let's rearrange that to go y equals, what do we get? X minus 3 over 2. So x minus 3 over 2, or y equals half x minus 3 over 2. Alright, so that is suggesting that's the equation that should kind of represent something looking like this green line. So over in Desmos, I had to go entering these equations before. So there's the red line, which is our original equation, y equals 2x minus 3, and then the equation y equals a half x minus 3 over 2 is that one there, which looks as we were expecting to. So we've taken the red line, we've rotated it by 90 degrees anti-clockwise, then we've reflected it across the x-axis, and that is what we've ended up with.